To our Design Lab 2 overview. I'm Jennifer, and joining me are my great teammates, James, Cecil, and Keegan. The goal of this lab is to improve our old production line by identifying major problems in our assembly structure and introducing new concepts for improvement. Enjoy! We will go over a brief description of the product, the original structure of the assembly line, the problems we encountered from the initial design, the proposed solutions based on those problems, the results of our implemented solutions, the cost-benefit analysis of proceeding with our suggestions, and the conclusion along with any unimplemented ideas. Our product is a simple job-made tape measure that can be assembled with 2 screwdrivers. The parts of the tape measure vary in size and definition. The tape can be used for measuring short and long distances during construction or household work. The tape may be used and retracted immediately upon measurement or held in place by a slider if necessary. The tape is available in both red and orange colors. The design of the original assembly line was built with 4 workstations, all adhering to a takt time of 24 seconds. The assembly line was built in a box shape, and on average, the total task time to build 1 tape measure was 80.7 seconds. With the original structure of the line, we were able to meet demand. However, there were some problems during the process that could have been improved.
Our group encountered several problems with Design Lab 1. First of all, the screws were very difficult to handle because of their small size. As a result, the operator wasted time picking up screws out of the parts bin and often dropped the screws on the workbench. It was also difficult to fasten these screws to the tape measure as they fell out of position in between wrist turns of the screwdriver. This increased overall cycle time and variance among cycles. The second problem with the screws was the similarity between the 2 smaller screws. They could be mistaken for each other, and even worse, they could be mostly fastened into the other screw's location. So if the operator unintentionally built the tape measure with the incorrect screws, then we found the clip could wiggle around, which is a quality concern. The next issue that we encountered with Design Lab 1 was the tape unraveling from its roll. This was a safety concern that endangered everyone's eyes. Also, the spring was not always centered in the roll, requiring the operator to position it with pliers. Both of these created a source of variation in our cycle time. Our next issue with Design Lab 1 was the deformation of plastic parts. After several rebuilds, the screw holes could be stripped or the rod upon which the tape roll was placed bent. This created several problems. Either the covers could not be fastened together, or the bent rod made it difficult to place the 2 covers together. The final issue that we identified is it was difficult to distinguish the correct orientation of the clip or tape roll. This led to wasted time as the operator repositioned parts.
The second solution that our group considered was a Toyota ideology called Poka-yoke. This translates to eliminate product defects by reducing unintentional human error. We decided to go with this solution, cost-effective to eliminate defects at their source rather than search for them at the end of the process. Statistical process control can also become a problem as it always allows some measure of product to slip through into the consumer market with defects. So our final solution to prevent the mismatch of the 2 small screws was to make the parts the same and therefore interchangeable. One of the major time constraints faced in the production line was the amount of time it took to screw the tape measure together and attach the clip. We cut down on this portion of the assembly by allocating a budget to purchase an electric screwdriver. The screwdriver also has a magnetic tip, which combined with the purchase of 2 screw dispensers had a huge effect on the takt time. Another piece that was implemented was the staple, which holds both the spring and the tape in place. This cuts down on the time it takes to wind the spring. The staple will also reduce the number of products wasted, as it will hold the tape together and prevent it from springing apart.
Up next, and most interesting of all, our data analysis. During our time trials, we simulated how the work would be done if the tools and solutions recommended in this video were in fact implemented. For example, the time to fasten the screws with an electric screwdriver was estimated by dividing the number of rotations necessary to fasten the screw by the rotations per minute of our screwdriver. With the data from our 30 trials, we performed 2 sample t-tests of unequal variances, where the null hypothesis was that the mean time before and the mean time after our changes were equal. Since task 12 includes all getting and fastening of screws and the clip, we had to aggregate tasks 6 through 10 by summing their means and variances. Both of our t-tests resulted in p-values of virtually 0, concluding that our solutions statistically reduced the mean task times. Other tasks whose method of work was not significantly changed were not retimed. Now, one comment on our methodology. The simulated trials may have an artificially low standard deviation. That's because there was no actual equipment used in our trials with which the operator could fumble or make mistakes. Those mistakes would be sources of variance. In conclusion, our solutions reduced the overall task time from 81 seconds to 39 seconds.
The cost-benefit analysis for our project is as follows. For the first improvement, we're going to buy a Granger tool retractor, which costs $130 with shipping. The benefits of this tool are that it will return the screwdriver to a preset position automatically after each use, and also the tool can be accessed by multiple users. The second piece of equipment we plan on buying to improve our process will be the Granger electric production screwdriver, which retails for $661. Benefits of this tool are precise torque application, which will be easier on the worker's forearm, and also a magnetized bit allows easy access of the screws. The final piece of equipment that we'll purchase to improve our process will be the Atlas screw dispenser, which retails from $500 to $2,000 depending on the custom order. This tool allows easy access of screws with the magnetized bit, and also screws can be released on a timer, which will improve efficiency. Our last improvement recommendation will be to lay off one worker. This will save a total of $22,568. Benefits of laying off this worker will be the reduced payroll cost and also the reduced personnel cost in the form of benefits.
One idea that was not selected for our final design was changing the peg that holds the spring from plastic to metal. The reason this idea was not implemented was because the quality of the pegs was only an issue based on us assembling and disassembling the tape measure multiple times. One other idea that wasn't implemented was replacing the plastic treads on the casing of the tape measure with metal ones. Again, this was an issue of quality of the tape measures being disassembled and reassembled multiple times as the screws stripped the plastic threads from the tape measure, and therefore was ruled out as a solution.
In conclusion, by redesigning the assembly line, purchasing new equipment, and reducing the amount of workers, we were able to reduce the total task time of preparing one tape measure from 80 seconds to 39 seconds. Thank you for watching our presentation. We hope you enjoyed it. Also, good luck on all exams. But obviously, we don't need it because we're the best IE group ever.